Good day, class. So I will for today give you the examples to the heat exchanger topics that we covered in class yesterday. So I'll give you two examples for the use of the temperature correction factor and the effectiveness method, and one example when you have a case of fouling and you need to consider it in your heat exchanger design. Okay, so allow me to share my screen. So we are now going to discuss, or I'm going to share to you the sample problems as found in John Copley's and McCabe, covering the topics that we have discussed yesterday. So for the first sample problem, you're given a 1-2 heat exchanger containing one shell pass and two tube passes that heats 2.52 kilogram per second of water from 21.1 to 54.4 degrees Celsius. Now, by using hot water under pressure entering at 115.6 and leaving at 48.9 degrees Celsius. So all four temperatures, if you notice, are given. The inlet temperatures of the cold and the hot water, the same thing with the outlet temperatures. So the outside surface area of the tube in the exchanger is given as 9.30 square meter. So letter A requires you to calculate the mean temperature difference in the exchanger and the overall heat transfer coefficient based on the outside fluid. Okay, and then for the same temperatures given in letter A, or the same working temperatures that are given in the problem, this time you are going to use a 2-4 exchanger. So you have a 2 shell pass and 4 tube passes in this case. Now you are to determine the delta T sub M, or that's the mean temperature difference. That way you can compare which of the two designs, the 1-2 heat exchanger or the 2-4 heat exchanger, utilizes the most of the driving force, and that is the temperature difference of your hot water. Okay, I will share a new screen so we can use our Jamboard for the solution of this particular problem. Okay, class, wait, huh? So for this problem, we need to write down the given information first, the very important temperatures, the area that we are to use. Okay, so we'll start with the given. So I will just open the copy of the problem. That way we need not go back to our PowerPoint presentation. So for this problem that we have, our hot water has this inlet temperature. So I will label it as T sub HI, and it's 115.6 degrees Celsius, and its outlet temperature is equal to 48.9 degrees Celsius. Now for our cold water, so its inlet temperature T sub Ci is 21.1 degrees Celsius, and the outlet temperature is given as 54.4 degrees Celsius. So 54.4. That's 54.4 class. Or let me just erase this one so it's clear. Okay, so you have that. Then you are also given, so based on our problem, you're also given the mass flow rate of the hot water. Or rather, this is the mass flow rate of the water that is to be heated. So this is the mass flow rate of the cold water, and that's 152 kilograms per second. And you're given the area. the outside surface area of your tubes to be 9.30 square meter. So in this cases, class, you are required to determine, in both cases A and B, you are required to determine the delta T sub M and the overall heat transfer coefficient based on the outside fluid or on the outside area. And for letter A, the scenario is you'll be working on a 1-2 design, one shell, two tube process. And for letter B, you're going to work on the 2 shell, 4 tube process. Okay, so this is our required information and these are our given information. So let's proceed on the next slide or next page of our solution. So we will now be finding out the required information. So for letter A, you are to determine the T sub M or the mean temperature difference. For this one, you need your temperature correction factor because your design now is a shell and tube heat exchanger, and you need the delta T lub mean. So you need to find these two. Actually, it's just direct substitution to the formula prior to getting the mean temperature difference. So we'll have this as our first equation. Then we go to our delta T lub mean. So for our delta T lub mean, we'll have this particular formula. So our orientation, by the way, it's very important to take note of the orientation in here. In the first one, it's 1, 2. So for letter A, it's 1, 2. And for letter B is 2, 4. Now, in this case, your delta T lub mean temperature for a shell and tube heat exchanger does not anymore need the, let's say, the mode or the direction in which the hot fluid flows in comparison to that of the cold fluid or the fluid to be heated. So in this particular design, your delta T lub mean formula will be based on this 4 temperatures. The inlet temperature of the hot fluid minus the outlet temperature of the cold fluid. And then we have the outlet temperature of the hot fluid minus the inlet temperature of the cold fluid. Whatever we have written here, we also copy on the denominator, which is our Ln. So the difference in the two temperatures in the numerator, you also copy in the denominator. So by the way, this is all. Okay. Now we go back to our given and substitute the temperature. So we'll not go back to the next page. So you'll have here your delta T lub mean. So 115.6 for the inlet temperature of the hot fluid minus 54.4 the outlet temperature of the cold fluid. Then we have 48.9 for the temperature of the outlet temperature of the hot fluid minus the inlet temperature of the cold fluid, which is 21.1. Whatever you have written there in your numerator, that would be the same thing that should appear in your denominator. So you have here a 48.9 minus 21.1. Now, if you're going to process this one, you'll be getting a delta T. So I'll write in here the value. A delta T lub mean of 42.3 Kelvin, or that's also equivalent to, I'll write it here, 42.3 degrees Celsius. Okay, so you have this delta T. Now, the next is you need to know the temperature correction factor. So if you recall, I'd like to go back to our slide. The temperature correction factor is dependent on the design of your shell and tube heat exchanger. So if I go back to our slide, So for letter A, we have a 1-2 design. So this is for a one shell, 2 tube passes, also applicable for 1 shell, 4 tube passes type of shell and tube heat exchanger. Now in here, for you to be able to get the temperature correction factor, you need the two shall I say, parameters here, X and Y. So we need to solve for these two first before we can use this particular graph to get the temperature correction factor. So let's go to our board again and continue and find the corresponding value of the Z and the Y. So for your Z, I'll just copy the formula here. That way we can directly substitute the informations that we need. So you have in the numerator the difference of the temperatures of the hot fluid, and in the denominator you have the difference in the temperatures of the cold fluid. Okay, now if we substitute values, this is 115.6 minus 48.9, and we divide this by 54.4 minus 21.1. This will give you a Z value of 2.0. As for the Y, so we'll base it also on the formula. You have in the numerator the difference in the cold fluid temperature, and in the denominator the difference between the inlet temperatures of your hot and cold fluid. So you have your numerator as the denominator of the Z a while ago. So we copy what we have here, and then we have 115.6 minus 21.1. In this case, you will have a 0.352. Now, if you're going to use this value of X and Y, or rather of Z and Y in the graph that was shown to you, let's go back to that graph. So if you're going to find the Z curve which is 2.0, it's this one. Let me annotate. And your Y value, your horizontal axis, for your horizontal axis, for your ordinate is 0.352. So 0.3, this is 0.4, this is 0.3, this is 0.4. So 0.35 is here, 5.2 is somewhere a little bit after that. So we go up, project it, and I think will be more or less here. Okay? This is the point, the intersection of the Z value, which is 2.0, and a 3 value, which is 0.352. More or less, your f of t in this case is, let me erase this, for a 0.352, this is 0.2, 0.3, 0.4, 0.35, 0.352, and you have a 2, it's somewhere here, plus a little bit after 0.35, so 0.335 is here. Okay, 352 is somewhere here. So in terms of approximation, somewhere here, high. And in terms of the value of f of t, it's around 0.74. Okay, if you follow the suggestion of the solution of John Cook, please. So if we have that, the 0.74, we go back to our solution. Your f of t, your temperature correction factor, is more or less 0.74. So the value of this is depending on you, the reader, on how you're going to read or what particular value you see would be the intersection of the curve 2.0 for the Z and the ordinate 0.352 for your Y. Okay, so if this is your temperature correction factor already, then your mean temperature difference will just be needing the product of 0.74 and your delta T log mean. your delta T log mean of 42.3. So you have here 42.3. So your delta T mean in this case will be 31.3 Kelvin. Okay. Now, you already so far determined the uh, delta T mean here in the required. So in terms of the U sub O, you have to think of the formula that you will be using where you can find the U sub O. And that formula would be the fundamental formula for heat transfer, which will be using the overall heat transfer coefficient. Since it's based on the outside area or in the outside fluid, then we'll have UOAO, and then we will have here the delta T mean, okay, or the delta T sub M. Now we know already this is given in the problem. The delta T mean is also solved already. Wait, is the area given already? Let me check. I was not able to write it there. Okay, so I think I was able to write our formula to be 3.9. Let me check. Oh, it's there. Rather 9.3 square meter. So that's our area. So we've checked it already. Now, before we can find the U sub O, we need to get the Q. Okay, so your U sub O actually is your Q all over the product of AO delta TM in this case. Now, this would be our equation 2 because we still need to find our Q. Okay, so our equation 1 a while ago is this. So we simply, this is from 1. Okay. Sorry about that, class. So we'll continue. So this came actually from our equation 1. Okay, now we go back to that. So we'll be needing the Q. That way we can determine the U sub O. So we know the fundamental formula for our Q. So your Q is equal to mCp delta T. Now, in the problem, do we have the Cp of water in this case? So since the problem is giving us water to be heated, so we can use the set of values for the, shall we say, for the cold fluid. Okay, the water to be heated. So we're given its mass flow rate. And by the way, this one class is also equivalent to mCp delta T of the hot fluid. Okay, let me just plug in, class. Sorry about that, class. I need to plug in. My laptop ran out of battery. So we have this. In our case, we'll be using that the properties of our cold water. That's the water to be heated. And this one. So that would be the same Q that we can substitute in the numerator of our equation 2. So your Q is equal to, so given in the problem is the mass flow rate of the cold water, which is 2.52. So 2.52 kilograms per second. And you have its CP, so we will assume the CP of water to be the standard CP, which is 1.87. In this case, for our Q, we will use for 4.187. So that's for the kilojoule. So kilojoule per kilogram Kelvin, and of course use the temperature change in your cold water. So the temperature change of your cold water is this, 54.4 minus 21.1. And this could be Kelvin difference or Celsius difference. So you cancel kilograms and the Kelvin, and you'll have a Q in kilojoule per second, and that's in kilowatt. So your Q in this case is 348.2 kilowatt, or that would be 348,200 watts. Okay, that's your Q. Then you just substitute the Q in equation 2. So from 2, you'll be getting a U sub O value, which is equal to 1196 watt per square meter per Kelvin. Okay, that is after you have substituted your Q here. Your AO is based here on the given is 9.3. And what else that you need to substitute here? And the delta T sub M, or the mean temperature difference, which already considers the temperature correction factor F sub capital T. So that's your U sub O if you have a 1-2 design for your shell and tube heat exchanger. But if you have a case of a 2-4 heat exchanger, they will only actually differ in the temperature correction factor. So using the same, by the way, we check on the one that we have in our slides. Let's go back to the slide. So be again exposed to it. So for the slide, this is for the 1-2 and 1-4 design. For the 2-4, you have a different set. For the Z, you have THI, and I think it's the same Z and the same Y formula, only a different graph to use. So the value of the Z that we have computed in letter A and the value of the Y will still be used for letter B because they still have the same formula in here. So using the same Z and Y value but a different graph, so this will be the corresponding value for your temperature correction factor. I will just simply take it from what's provided in here. So it's around 0.94, which gives us from equation 1 again a delta T mean value Ft times the delta T lub mean temperature of 39.8 Kelvin, or that's 39.8 degrees Celsius. And if you determine the U sub O in this case now, the same Q, your U sub O will give you 1196. So sorry, that's for the letter A still. If you're going to determine the delta T mean, you have this one already. Your U sub O would be using the formula same formula that we had in letter A. So Q over AO delta T mean. So your Q is the same value that we have in letter A, 348,200. An area of okay, we did not substitute the formula in here, so we'll get it in our given. So you can see the substitution. So we have 9.3 and a delta T mean of 39.8. So this will give you a different U sub O. So we'll check the corresponding value of the U sub O, class. 348 200 divided by 9.3 and 39.8. So you will have a different use of O as expected because your delta T mean also changed. So you have a 940.725. A 940.725 for your overall heat transfer coefficient. So this is in watt per square meter Kelvin. Okay, so again, we will have it computed. 348,200 we divide by 9.3 and we divide by 39.8. So we have 940.725 watt per square meter Kelvin. Now, what is worth noting, class, in this particular sample problem that Jan Kuplis worked out for us is that the delta T mean for scenario A, wherein you have this delta T mean, 31.3, is lesser than the one in which the design is 2 shell 4 tube process. So your delta T mean is 39.8. So 39.8 is greater than 31.3. So we can say that the second design, the 2-4 design, makes use of the temperature driving force more effectively or efficiently, meaning it makes the most of the heat transfer available, the heat transfer area available for greater amount of heat to be transferred from the heating fluid to the water that is to be heated. So the more tube passes, the more shells we have, the greater is the amount of heat that is transferred because of this one. Your delta T mean is also increased. So that's for our sample problem, number 1 for this heat exchanger topic. Now we go back to our slide, so we'll have the second sample problem. Okay, so this is the illustration for the first sample problem. You have one shell and 2 tube passes, okay? For number 2, so this is the case wherein, of course, we will utilize the effectiveness concept because we don't have the complete set of the 4 temperatures, okay? Now, in this problem, water is flowing at a rate of 0.667 kilograms per second, which enters a countercurrent heat exchanger at 308 Kelvin and is heated by an oil stream. So you have water to be heated by oil. So the oil has an entering temperature of 383 Kelvin at a rate of 2.85 kilograms per second. The CP of the oil is 1.89 kilojoule per kilogram per Kelvin. And the overall heat transfer coefficient is given as 300 watt per square meter per Kelvin. The area available for heat transfer is 15 square meters. So we are to calculate the heat transfer rate and the exit water temperature. The heat transfer rate, so that must be our Q, and the exit water temperature. So let's go to our board and write down the information that we are provided and work out this problem. So this one is our first sample problem. And this one is our second sample problem. So for this problem, we'll write down the given first. So we can see what's the set of data that we can work out. Is it complete? Or now you will see the reason behind why we need to use the effectiveness method. So we have for water, so that's for the fluid to be cooled. So you have this mass flow rate, 0.667 kilograms per second. And we'll be using here a counter current heat exchanger. So that's a shortcut for that. Counter current heat exchanger. We'll use parallel heat exchanger for co-current. Okay, and then this water enters the heat exchanger at a temperature of 308 Kelvin. It is to be heated by an oil stream. So you're given an oil stream and you're given here the mass flow rate of the oil stream. So the oil stream is our heating medium. So I'll place here mass flow rate of the hot fluid, which is the oil, and it's 2.85. Okay, we're given its temperature of the hot fluid, 383. Now we're also given the CP of the hot fluid, 1.89. So this is kilojoule per kilogram Kelvin. We're provided with the overall heat transfer coefficient, 300 watt per square meter per Kelvin. And we're provided also with the area available for heat transfer, which is 15 square meter. Okay. 1, 2, 3, 4, 5, 6, 7. 7 information. So we have 5, 6, 7. Okay, so that's it. And we are given a counter current heat exchanger in this case. Not even mentioning about whether it's a one shell, two tube pass, or not even mentioning whether our heat exchanger is double pipe. So it simply is saying that the direction in which your hot fluid is in comparison to your cold fluid is counter current. So they're flowing counter current to each other. Okay. Now it is in problems like this that you have to check whether the first technique or the first method is applicable, and that's the temperature correction factor method. That tells you that it's not because number one, the orientation is not given, whether it's 1, 2, 1, 4, 2, 4, 3, 6, or something like that. It's not given. And one thing that is worth noting is you're only given two temperatures. Both are inlet temperatures. So if you are to use the temperature correction factor method, you should be provided with all four temperatures. So in this case, we cannot use that particular method in determining what the problem requires, which in this case, our problem requires for the heat transfer rate and the exit water temperature. So if it's the exit water temperature, we'll label that as TCO, the cold water outlet temperature. So these are the given information for this problem. So we'll proceed to the next. Okay, so we'll go to the solution of this problem. Okay, since we are not given the outlet temperature of water, okay, we're not given the outlet temperature of water, the same thing with the hot fluid, we will first assume it and later on check whether our assumption is plausible or acceptable. So in this case, John Copley suggested that we start with the value of the outlet temperature of water, for the outlet temperature of water, which is 370. Of course, he knows that the answer would be near this one because he's the one who made the problem in the first place. But if your answer later on will be far from this one, then you have to assume a different temperature. Now the question why do you need to initially make an assumption for the outlet temperature of your cold water? Because whenever you're using the effectiveness method in determining the unknowns for your heat exchanger problem, especially with the design of such heat exchanger, the CP the CP of the, in this case, that would be water, of the cold fluid will be based upon the average temperature of such cold fluid. So in this case, your CPC should be based on the average of the inlet temperature of the cold fluid, which is 308. So that would be TCI, TCO divided by 2. And the temperature that you're going to get here would be, so if you'll have 308 here, plus, and you have TCO of 370, we divide it by 2. So you will have a corresponding CP here, the mean of the two temperatures of, rather, the mean temperature first of 339 Kelvin. And that's where your CP for the cold fluid should be based on. That CP for our water, our cold fluid is, I'll just copy it here so we will save time, is 4.192 kilojoule per kilogram Kelvin. You can get this in any appendix of your books, or your, better yet, you use your handbook. That way you'll be familiar on where you're going to get the CP of different fluids and even of other materials as well. So if you have already the CP of your cold fluid, then the next thing that you do when you're using the effectiveness method is you find the C minimum, which is supposed to be your C minimum, the product of the mass flow rate of the cold fluid and its CP. Then you also check for C maximum. Okay, determine for this, and this one, your C maximum, is the product of the mass flow rate and heat capacity of the hot fluid. So we go to C minimum. So mass flow rate, I'll just take it here. That way I will not have to go back to the slide. So your CP for the water, C minimum in this case, wait, class ha. So that would be 4.192 as we have here taken it. So you have 4.192. We multiply it with the mass flow rate. So the mass flow rate of our cold water is 0.667. For the C maximum, its CP for the oil as given is 1.89. The mass flow rate for this, it's better if this way because I will not have to read from the problem. Again, 2.85. So you will have these two C value, the C min and the C max. So if you compute the product, your C maximum is 5387 watt per Kelvin, and your C min, CC, 2796 watt per Kelvin. The reason why you need to get this is you get the ratio of the C min to C maximum as needed in the graph that we will be using for this particular method of the use of the effectiveness. So you have 2796 divided by 5387. So the ratio of C minimum to C maximum is 0.519. Okay. Now, you remember this formula? We have the number of transfer units, the NTU, which we can determine or solve using the product of the overall heat transfer coefficient and the area divided by the C minimum. So true to itself, true to what we have computed in here, class, the product of the mass flow rate and the CP of the cold fluid is really lesser than the product of the Same thing, the mass flow rate and the CP, or the heat capacity of the hot fluid. So in here, we're going to substitute the C minimum and the U and A values that is given in the problem. So your U is 300, your A is 15. Your A is 15 with a C minimum of 2796. So this would give you an NTU of 1.607. Okay, you need this NTU in the graph. So I'll show to you the slide where we discussed this yesterday for recall. Okay, so in the graph, you have actually two different graphs to choose from. So one will be for counter current flow. In that case, this is the one that we're going to use. And one for parallel flow, this one. Okay, now we computed the ratio of the C minimum to C maximum because the curves here in our graph are based on that. And we also determined the NTU. We determine this too, that way we can get the effectiveness. Now, if we already have the effectiveness as a review, so this is how you're going to solve for the amount of heat that is transferred. So you have rate of heat transferred is equal to the effectiveness times C minimum times the difference of the two inlet temperatures, that of the hot fluid and that of the cold fluid. So that's the reason why we need to get this from the effectiveness from the table. So if you go back to our table and based on the ratio of the C minimum to C maximum that we got, that's 0.519. So this is your 0.2 and this is your 0.75. It's not shown in here, class, but if you're going to look at it, it might be somewhere here, the 0.51. Okay, somewhere here or this graph. I think this is your 0.5, so a little bit above this one. You'll be the one to approximate that one, and you use the NTU as well, which is 1.607. So this is your 1.5, this is your 1.75, 0.67 must be somewhere here. You go up, you project that particular value in here until you reach the curve, which is more or less 0.51. Okay, that will give you an effectiveness here of more or less, this is your 0.7, and based on the data given to us, this is your 0.5, so it's 0.71. Okay, so this is the 0.71 in here using 1.607 and 0.51, so 0.71 for the effectiveness. Okay, I'll go back to our board, our solution. So from the graph, so using NTU and C minimum to C maximum ratio, you'll be getting an effectiveness more or less equal to 0.71. Now, with that effectiveness, you can determine now the rate of heat transferred. So I have shown to you the formula. So that would be effectiveness times the minimum, the C minimum times the difference in the inlet temperatures of the hot and cold fluid. So with the effectiveness that we have, which is 0.71, we get the C minimum that we have here, that's 2796. And the two inlet temperatures. So I'll get it from in here. 383 for the hot fluid and 308 or 308 for the cold fluid. So you will have a Q which is 148,900 watts. So that's your Q. Okay, now let's see what is the other information required. So you have the Q. Now how do you check the TCO? Whether the assumed value that you have for the TCO is acceptable. So what you're going to do is equate this value that you have with the formula that we have like this, 148,900. So that would be, I'd like to go back to the slide so you will recall the formula. Anyway, it's still fundamental though. It's a fundamental formula for heat transfer. This one, wait, this one, okay? We need to check whether the outlet temperature that we have assumed for our cold water is acceptable. So your Q, the amount of heat transferred, is actually solved using this one. But it's also the same or equal to whether you use this formula or this formula. In our case, we will be using this particular formula, which is still actually MCP delta T in your thermodynamics. So we go back to our solution and check whether that would be, so you'll have here C minimum because we're talking about the product of M and specific heat of your cold water. So that's C minimum. And you have TCO minus T, oh sorry, that would be TCI. Okay, so you'll have your C minimum again. So the C minimum, so it's really being used in here, 2796, used for the third time already, TCO minus the TCI. So your TCI is 308. I'll just copy it from the value that we substituted on top. In here, with this one, so this is still 148,900. So your TCO in here is equal to 361.3 Kelvin. Okay, the value that we have assumed is 370. So if you're going to check for the error, what's the percentage error for this? Let's see. So we have a 370 assumption, and then we have this value divided by, that will give us a percent error of 2%. The error for this is around 2.41% if compared to this computed value of the outlet temperature of water. If you think that this is still high, because it depends really on you whether you're comfortable with an error of 2.41, maybe you want it lesser than 1% error, then you can make another assumption. So this time I suggest that you assume a value which is in between 370 and 361. Because you have to bear in mind, class, that your C minimum here that you are substituting also in here, that you are equating to your 148,900 is dependent on your assumed outlet temperature of water, which you use in determining the original specific heat capacity of water based on the average of these two temperatures. So if you want to make another assumption, that way the TCO that you'll be getting later on will be nearer or will be having a percentage error of less than 2% or make it 1%, then you may suggest a temperature that is lesser than 370. Probably 365 or something like that, and then do this. Normally, class, a second trial will already be more acceptable than the first, but this one suggested by as given by the author of the book would already be acceptable. Okay, so remember, so there are things that you need to remember when you use the effectiveness method. Your CP for the fluid is based on, if it's not given, is based on the average temperature of the fluid. So in most cases, if it's an effectiveness method that you use, your outlet temperature is not given. So there's a need for you to really make an initial assumption. So that's the thing. And then you have to take note of the mode of contact, or of the, no, not the mode of contact, but rather the manner in which the fluid to be heated flows, in what direction that it is flowing. Is it flowing against or parallel to the one that is heating it or cooling it down? So you have to take note of this, the orientation. Okay, And that's it for our second sample problem using the effectiveness method, using the graph, which needs for you to make an assumption for the outlet temperature of the cold fluid. So we go back to our slide for the last sample problem, which will be this time taken from McCabe, because the first two were taken from John Copley. So this one we will take from McCabe. John Copley this time did not discuss anything, did not give a sample problem concerning fouling, for how you take into your design equation the presence of the fouling material in your heat exchanger, both in the inner part and in the outer part of your tube. So this was shared to you. The way we account for the fouling, this one, HDI and HDO. Now, since we're using a sample problem from McCabe, before I go to the sample problem, I'll give you the formula that McCabe uses in determining the overall heat transfer coefficient, whether it's based on the outside area or in the inside area of your tubes, now accounting for the fouling factors. On the inner part of the tube, so you have this H sub DI, and the outer part of the tube, which is H sub DO. The D's that you are seeing here refers to the diameter of your tube, and then this one is the lube mean diameter, the D with the bar on top. That's the lube mean diameter, comparable to the lube mean radius, which will be shown to you in the solution later and how you're going to make use of it. The X here in McCabe, so if you're going to study heat exchangers also using McCabe, to complement what you have in John Copley's, this one is the thickness of your tube or your pipes, and K, of course, is the thermal conductivity. Okay, and that's it. So this will be your formula if it's U sub O that you need. This will be your formula if you'll be needing U sub I. Okay, so this is our only sample problem that accounts for fouling found in McCabe. So it's chapter 11, as you can see here, and I'm using the latest edition of McCabe. So in here, given that methyl alcohol is flowing in the inner pipe, take note of a double pipe exchanger. So we're not talking about a shell and tube because it's specified in here that we have a double pipe exchanger. This methyl alcohol is being cooled by water flowing in the jacket. So meaning it's the outer or outside fluid. Now the inner pipe is made from 1-inch schedule 40 steel pipe. Your inches unit was just converted here to millimeters. The thermal conductivity of steel is 26 BTU per hour per foot per degree Fahrenheit, and this is the equivalent in SI, in watt per meter per degree Celsius. Now, the individual coefficients and fouling factors are given in the table below. So the heat transfer coefficient for alcohol, your inner fluid, is labeled as H sub I, and this is its coefficient in English, and this one in SI, set of units. So you were also provided that for water, your outside fluid, which cools down your methyl alcohol. And you have this heat transfer coefficient by based on the inner fluid through the inside fouling factor, and this one is based on the outer fluid water. So you have the corresponding value of the H in here, because actually in the nature of the formula that we have for the consideration of the fouling factors in the design of heat exchanger, all you need to do is substitute. Okay, so based on the formula that was shown to you a while ago, because the same U will be then used with this with area and the delta T mean for you to be able to find the heat transfer rate. Okay, now, so your diameter and wall thickness for a 1-inch schedule 40 pipe is given in the book by McCabe on Appendix 3. In your case, I have also shown it to you on how you're going to read it from the appendix of John Copley's. Now you check in your handbook on how you're going to get this particular information, the diameter and the wall thickness based on the size. We call it actually the nominal size of your pipe and its schedule number. So for a schedule 40 pipe, and this with a 1-inch nominal size, this is your inside diameter, this is your outside diameter, and this is the thickness. So since primarily this problem is working on English units, so this values for the diameter and the thickness are all in English units. It also follows that the heat transfer coefficients that we're going to substitute to our formula later on will also be based on this first column here, wherein we have English units, sets of units. Okay, now the logarithmic mean diameter, which I have mentioned here, the log mean diameter is comparable to the formula of the log mean radius. And for this log mean diameter, you have the outside diameter minus the inside diameter divided by the ln of these two, outside diameter and inside diameter. So we'll just substitute the diameter values that we got from the use of the schedule number and the nominal size of our tube in this formula, and the rest is a substitution to the U sub O. So it is worth noting in here, class, that without considering the fouling factors, you should only have actually 3 terms in here in the denominator, as discussed to you last meeting. Now, the ones that you have in here in your denominator is, or the values that are reflected in your denominator will just we're just the product after we have substituted. Oh, sorry, where was I going? After we have substituted the values to this formula in here. Okay, so you have, in our case, we're determining the overall heat transfer coefficient based on the outside area of the pipe. So the formula that we use is this one. So you need the outside rate, the diameter, inside diameter, and this fouling factor based on the inside part of the tube, and all of the rest are all substitution to this formula. And in our problem, the value for that in English units will be this, and this will be the corresponding value for the SI sets of units. If we did not consider the fouling factor, class, we will have a higher value. We will have a higher value for U sub O, because it's expected that fouling factors will decrease the amount of heat that is being transferred to our fluid. Okay, so that's it for the topic of the heat exchanger, class. So feel free to message me if you have any question concerning the sample problems that were discussed to you in this set of slides. Okay, bye for now.